Let's start with the liquid to solid transition. Definitely don't go shooting dangerous chemicals at high velocities. Finally, we have our sort of insane multi-dimensional pro and con list for liquid to solid transition approaches. No, please. The amount of math required to understand the answers is too much for how philosophically unexciting the questions are. No! Welcome back to Dragline Dynamics, everybody. Let's jump right in, because we have a lot to cover today. A lot of math in particular. But don't let that scare you. Math is an absolute necessity when it comes to this stuff, and you can learn to enjoy it if you don't already. So once we've conquered the liquid to solid transition, are we done? Of course not, you dummy. We've never really seen Spidey just ooze some goo out of his wrists, right? I mean, it's a web shooter, not a web dispenser or a web spinner even. And that makes everything much more complicated. We've already discussed briefly the production of nylon, where the polymer created is very, very strong, but has to be manually pulled from the chemical bath and wound around a spool as a fiber. This method of synthesis would not work for web shooters. Actually, this is a very common production method for materials like this. Oftentimes, a special dye called a spinneret, crazy, yes I know, like a spider, wow, is used to force whatever solution is being used through tiny holes to create the fiber. And a variety of methods are used to solidify it. But this is a very, very, very slow process, not really the behavior we want. The same thing goes for the deposition of viscous fluids that are intended to cure, usually into elastomers, which is just a fancy name for stretchy polymers like silicone or polyurethane. An example of this is the silicone caulk that you would use to seal in your shower or bathtub. The properties of this material are decent and could be considered web-like, but with a viscosity that high, there's no way you'll ever shoot that to a range of more than a couple inches, let alone across a room. Now, range and exit velocity are related in a very simple way. If you've ever taken a physics class, you would know this. Any massive projectile under the influence of gravity, whether it be a ball or a feather or a particle of web fluid, follows a parabolic trajectory. Now, assuming there are no other forces present, like drag or surface tension, which are good assumptions for small solid objects. Now, when we look at the definitely spherical Earth very closely, the ground looks flat. And that's the sort of range we're most likely going to be using web shooters in, unless you get some sort of cosmic web shooter. Gravity will always act towards the center of the Earth, which in the scale is a direction that presents itself as always downward. Our coordinate system directions, x and y, will be used to differentiate between the horizontal and vertical directions. Since gravity only acts downward, it will only affect the vertical velocity of the projectile, accelerating it towards the ground. The horizontal velocity remains constant, and the parabolic trajectory results. The range is usually measured as the horizontal coordinate at which the projectile's vertical coordinate is 0, or when it hits the ground. The x-axis intercept, if you want to call it that. If you're finding the projectile horizontally, you can find the range by first finding the time it takes for the ball to hit the ground, which is only dependent on the initial y component of velocity and the gravitational acceleration and the height at which it is thrown. Then you will find how far the ball will be able to go horizontally during this amount of time, which you can find by multiplying the horizontal component of the velocity by the time to impact. From the simulation you see here, we can gather that there are many ways to increase the range of a projectile, by either increasing the vertical height at which it was launched, or increasing the exit angle, but we don't always have unlimited height, and the angle increase only helps up to a certain point, until the projectile motion becomes more like an upward throw. What we can see is that increasing the exit velocity is always beneficial to the range. Of course, we won't always be aiming our web shooters at ground targets, actually almost never, and we would much rather hit the thing we're pointing at, right? I mean, as hard as gravity makes that. So a much more realistic way to evaluate the range would be to define a tolerance for how far away the projectile hits its intended target, which is something that the exit angle defines. Oh yeah, we are sharpshooters, baby. A target allowance, if you want to call it that. Increasing the target allowance increases the range, but decreasing it means you have to be more precise, and the range decreases. Here we see that the range is much less than it would be should we want it to hit the ground, so we clearly have to add a lot more exit velocity for the projectile to shoot somewhat straight. Which makes intuitive sense, but is supported by the math. Stay in school, kids. So long story short, Exit velocity isn't just about speed. It actually will define how far your web shooter will be able to shoot. As for the extrapolation of projectile motion to something like a fluid stream, let's just take a look at this experiment. I'd say that liquid looks, pretty parabolic to me. So how can we increase our exit velocity? Well, now we're getting into classical fluid dynamics. Let's start with the introduction of what we call an ideal fluid, which is incompressible and inviscid, or has no viscosity, and whose flow is always irrotational, i.e. there's no turbulence. If we look at ideal fluid flow through any geometry, we know a couple of things for certain. If the flow is steady, that is, the velocity and other quantities don't change with time, the incompressibility of the fluid tells us that the flow rate at the inlet is the same as the flow rate at the outlet. This is called continuity, and it can be seen that a constant volumetric flow rate means faster velocities for smaller pipe diameters. So one way to increase our exit velocity would be to decrease the diameter of our nozzle, but we will soon see why this is not always the best way. Now, Bernoulli's principle also comes into play with ideal fluids. For those who are unaware, Bernoulli's principle brings the universal law of energy conservation into fluid dynamics. When any system in the whole universe undergoes a process, the amount of energy at the end of the process must be equal to the amount of energy at the beginning of the process, plus the amount of energy transferred to the system, and minus the amount of energy taken out of the system. The same applies to fluid dynamics. At the inlet, the fluid has a certain kinetic energy equal to its mass times its velocity squared, and a certain gravitational potential energy equal to its mass times its altitude times the gravitational acceleration. At the outlet, the fluid might have a different kinetic energy and a different potential energy, but if no energy is added to the system, or in other words, if no work is done on the system, the total inlet and total outlet energy should equal each other. So how do we do work on a fluid system? You may have learned in physics class that work is doing a force over a certain distance. For instance, if you want to push a block over a flat surface with ordinary Coulomb friction, at the beginning the block is stationary and at an altitude, and at the end the block is stationary and at the same altitude. So the total energy in the system did not change. So the net work done on the system is zero. However, we know that kinetic friction was acting on the object throughout the entire distance, opposite to the direction of motion, at a constant value of the normal force the surface exerts on the block multiplied by the coefficient of friction. Since frictional force acts opposite to the direction of motion, the friction is doing negative work on the system. So to keep the net work zero, I must be doing positive work on the system, equal to the sum of each little movement I did multiplied by the force I was exerting through that little movement. You'll probably recognize this, if you've taken calculus or physics, as the integral of a force along a path with respect to the amount of distance traveled, or the integral from the beginning of the path to the end of the path of f.dl. If f is constant, as it is in the block example, this simplifies to simply f times L, where L is the length of the path and f is the constant exerted force. But the integral is far more powerful in both usage and understanding. So back to our fluid system, how do we do work on it? I want you to first imagine a piston trying to compress a fluid. Now, assuming no friction in the piston, the pressure in the chamber will be exactly counteracting the force exerted on the piston. That is to say, F equals PA. But the force and pressure are not constant. They may be functions of the distance traveled, i.e. F as a function of L is equal to P as a function of L times A. Imagine the piston moves a really small amount. We know that the area is equal to the little bit of volume that is taken by the piston dV divided by the little bit of distance that the piston moved, dl. If we multiply both sides by dl, we end up with this. And this should start looking familiar. The work done by the piston can be seen by integrating both sides as the integral over a volumetric change process of the pressure throughout the process. The units of force times distance are also equivalent to the units of pressure times volume. So back to Bernoulli's equation, where we were trying to figure out how to represent work done on a fluid in flow. Essentially what we saw in the piston example is that pressure changes can do work on a flow. So adding a pressure difference to the inlet side multiplied by volume gives us the work done on the system. And the outlet energy should be higher if the term is positive, i.e. the pressure at the inlet is more than the pressure at the outlet, which makes intuitive sense. Now, some of these terms still look a bit weird. I mean, mass of the fluid doesn't really make sense as the fluid is continuous, and the same goes for volume. It is only after we divide by volume and see the true nature of Bernoulli's equation, I mean, it's incredible how perfectly this principle is intended for fluids, as density becomes a representation of how massive a fluid is in order to calculate kinetic energy. Looking at Bernoulli's equation, we can disregard some terms when it comes to web shooter. The mass and the height difference of the fluid at the inlet and the outlet are not really going to justify looking at a difference in potential energy, as the most height difference you can get is just like the length of a human arm. So we're just left with comparing the velocity at the inlet and the outlet with the pressure difference between the inlet and the outlet. In order to have a higher outlet velocity, we need to have a higher difference in pressure between the inlet and the outlet, with the inlet pressure being higher. This also makes intuitive sense, I hope. So for an ideal fluid, we can decrease our nozzle size and increase our pressure difference to get a higher velocity. But remember, this is when ignoring a fluid's compressibility, viscosity, and turbulence. It turns out that assuming incompressibility is more than sufficient when modeling liquids, which applies to web fluid, even if there may be some gas bubbles from the vapor phase of the propellant, which could allow it to compress a small amount. Turbulence and viscosity, however, are sort of mutually exclusive. You'll often see highly viscous fluids like honey acting without any apparent turbulence, behavior we call laminar. On the contrary, you'll see very low viscosity fluids like air having a whole lot of turbulence. One way to quantify this is using something called the Reynolds number, which has no units but is simply a ratio between inertial forces increased by quantities like mass and velocity, or in the fluid case, density and velocity, and viscous forces increased by viscosity and decreased by the scale of the flow. The L in the Reynolds number equation here is a measure of the scale of the flow and is called the characteristic length. For pipe flow, this can be chosen as the diameter of the pipe, called the hydraulic diameter. If the Reynolds number is high, above about 50,000, the flow is likely turbulent, but also easier to approximate as inviscid. If the Reynolds number is low, below about 2300, the flow is likely laminar, but also likely requires viscous effects to be taken into account when modeling. Remember, viscosity is like friction in the fluid, so we can expect it to do negative work on the flow, just like the Coulomb friction did in our block example. In the ideal fluid, the only way to change the velocity, and as a result the pressure, from inlet to outlet is by changing the cross-sectional area of the pipe. But with viscous effects for a non-ideal fluid, we can expect a pressure drop across the length of a constant diameter pipe. This is called fully developed flow, or Poiseuille flow in a pipe, named after Jean Poiseuille. The derivation of fully developed pipe flow comes from the Navier-Stokes equations, which is a system of partial differential equations that can describe many fluid flows in 3 dimensions, but due to its nature can't be solved by hand in most cases. Simulation softwares utilize numerical methods to solve these equations and compute how fluid might flow in a geometry due to certain boundary conditions. The Navier-Stokes equations defined in Cartesian coordinates are shown here. We have the continuity equation, which describes the compressibility of the fluid, and the 3 momentum equations, which are basically Newton's second law in fancy form, that the net force at some location in the flow equals the mass times the acceleration at that location in the flow, for 3 orthogonal coordinates. Navier-Stokes equations are also defined in cylindrical coordinates instead of x, y, and z, where location is defined as a distance r away from a center axis, a distance z along the center axis, and an angle theta away from some reference point. Fully developed flow means what its name sort of suggests, that it's been flowing through a pipe long enough that it no longer changes with time. That is to say, it's a steady flow, it no longer changes with time, and it no longer changes along the axial direction, so all the dt's and dz's can be set to 0. And since the flow is incompressible, we set this value, called the divergence of the velocity field, to 0. You can think of this as saying all the velocity vectors must be part of streamlines that converge to the outlet to preserve a steady mass flow. And for fully developed flow in a circular pipe, we don't expect there to be any changes in the angular direction, so all the d thetas can be set to 0. Suddenly, we're just left with derivatives with respect to one variable r, the radial direction. We now have an ordinary differential equation instead of a partial differential equation. Basically, what we're looking for here is how the velocity of the flow changes as you get farther from the center and closer to the walls, or the function u of r. Yes, u is velocity, I know, that's just a convention. Solving the differential equation for this gives us a distinctive parabolic velocity profile. Integrating over the whole cross-sectional area of the pipe and dividing by the area gives us an equation for the average velocity of the fluid. a version of an equation called the Hagen-Poiseuille equation, which describes Poiseuille flow through a circular pipe. Looking at this equation gives us things that we can change to improve the velocity at the outlet. We can either increase the pressure difference or size of the pipe, or decrease the length of the pipe or the viscosity of the fluid. This is something that's easily imaginable and even testable in the real world. So what tools do we have available to us? Increasing the pressure difference, essentially increasing the force on the fluid, seems like a surefire way to increase velocity, right? It turns out that tool isn't always available to us. For instance, oftentimes a propellant in a web shooter will exert a constant pressure on the inlet of the system, at the exit point of the fluid reservoir or canister. This means that the pressure difference between the vapor pressure of the propellant and atmospheric pressure at the outlet cannot be altered. What about the diameter? Now, increasing it may actually lower the velocity, especially if you're just using it at the nozzle to direct the fluid. I mean, remember continuity. The diameter could be small enough such that it's restricting the flow velocity through viscous effects, but if it's too large, the volumetric flow rate will be unhindered by viscous effects, but the large cross-sectional area will lead to a low flow velocity, and you'll just end up oozing goo, as presented earlier. I would try to increase the diameter before the nozzle though, and keep as much space as possible for the fluid to flow. The length of the pipe could be minimized for sure, but some people like myself prefer web shooters where the canister is somewhat removed from the valve for aesthetic purposes. Obviously, reducing viscosity is important, and that's why many of us opt for a more diluted web fluid. But if we were unhindered by that, we could have a higher polymer concentration and potentially stronger webs. But are these all the options we have? I mean, let's take a look back at the Hagen-Poiseuille equation. Remember that this equation only describes fully developed fluid flow through a circular pipe, and it does so through the viscosity or friction, the pressure difference or the input force, and the geometry of the flow. Cylindrical pipes are just one of many flow geometries, and there's one critical part of the web shooter that will almost certainly not have a cylindrical flow, and that is the valve. Now, valves generally have complicated geometry, like this solenoid valve, which I used to use for web shooters years ago. One of the only valves that has cylindrical geometry when it is open is a ball valve, and those are generally not fast acting and require a lot of force to open, so not a good fit for a web shooter. Now, over the last few years, the human spider and I have been hard at work developing valves that are specifically designed for web shooters, essentially trying to minimize dead zones where fluid has low or zero velocity and could solidify without leaving the nozzle, and trying to minimize the friction of the flow by improving the geometry. It's not easy by any means whatsoever to analytically model non-cylindrical flow geometry, especially if it has a changing cross-section. Usually, computational fluid dynamics simulations are used, where a computer solves the Navier-Stokes equations mentioned before. Using this, we can quantitatively compare a few different valve geometries. Remember this valve, the one I used that you were all so impressed by? Its basic design can be attributed to the human spider, and it seems to work very well. However, I never knew what it was like inside, so I decided to precisely measure each component and model the assembly in the computer. Once I did that, I can clearly see that there's limited space for the flow, so it could be constricted. That, and there are these bumpy areas from the threads on the brass pieces, which lead to dead zones, but also to more friction due to an equivalent pipe roughness, another factor in non-ideal fluid flow. Here is a simulation geometry equal to that of my web shooter. It includes the long tube leading from the canister to the valve. It includes the valve itself all the way to the nozzle of the web shooter. We will model a steady flow in the open position of the valve, so we are not taking a look at what we call transient effects, basically the acceleration of the fluid. We're only evaluating the maximum steady state velocity of the web fluid. Now, I'll give this simulation a boundary condition of a pressure drop of about 564 kilopascals, which is 665 kilopascals, the vapor pressure of tetrafluoroethane, my current propellant, minus 101 kilopascals, atmospheric pressure. After the Navier-Stokes equations are solved in the simulator, we have a velocity field, which gives the velocity components u, v, and w in three respective coordinate directions, x, y, and z, at discrete points throughout the geometry. Here we can see the magnitude of the velocity. Because we want to evaluate the exit velocity of the web shooter, we will take a look at the discrete points very close to the outlet. Here we have these discrete points plotted as the x and y position that the velocity is occurring at, and the z component of the velocity w. Here we can make a hypothesis that the flow at the outlet of the circular nozzle has a fully developed parabolic velocity profile. If this is the case, we should be able to fit this surface function to these points. We can convert from cylindrical coordinates to the Cartesian coordinates our points are plotted in by substituting x squared plus y squared for r squared. It looks like this surface fits the points fairly well, so it's safe to say we have a supported hypothesis. This gives us values for both the fraction delta p divided by 4 mu l and the radius r, and these can be used to find an estimation for the maximum flow velocity at the output, and the average flow velocity, which is just half of that. An argument can be made to use either of these as the speed of our web line. From here on out, we're going to be using the maximum velocity because on this channel we like to oversell the success of our inventions, but I'll still show the graphs for both maximum and average velocity. So for the original valve geometry, we can see the maximum outlet velocity reaches about 12.9 meters per second. According to our range calculator, when firing horizontally, the fluid will hit the ground a little over 7 meters away, and it'll be able to hit a target a meter in diameter about 4 meters away. So let's see what we can do to improve the inner geometry of our valve to decrease friction and hopefully allow a higher outlet velocity. Looking at some simple modifications like smoothing out the threads by either making the inner chamber thinner or wider shows that making it wider yields a slightly better result, but only when the spring is removed. In the case of the original valve, removing the spring from the geometry actually decreased the output velocity slightly, which did not support a hypothesis I had that the spring increased friction with the fluid. However, doing the same for both smoother versions did support this hypothesis. The increase is so small that it appears that the spring geometry makes little difference. All of these different geometries did little to improve the valve friction, if at all, with the only actual improvement being the wider version with no spring. I then decided to compare this with what I considered the ideal valve, which is just a simple pipe section where the diameter gets reduced and the fluid is allowed to flow straight through its entire path. This showed a slightly better result, with the fluid now reaching a new record output velocity of about 13.2 meters per second. The next step was to make the actual valve better. This is the design for the flow geometry I came up with. It has less room for dead zones, with the fluid diverging off at a less aggressive angle, and then also converging at a less aggressive angle. I tried to keep the cross-sectional area of the fluid's path as large as I could before it reached the nozzle section to prevent any unnecessary restriction on the fluid. This flow geometry showed a much better result, with the outlet velocity now reaching around 13.9 meters per second, and this is without altering the inlet and outlet diameter, just the internal geometry. My next task was to see what else could be done to further improve outlet velocity. Remember what I said before about the reduction of nozzle diameter sometimes helping and sometimes hindering the outlet velocity? We can actually see this in my next set of simulations, where I vary the nozzle diameter between 25% and 100% of the original. We can see our outlet velocity start to increase as we lower the nozzle diameter, but at a certain point it starts decreasing as the flow gets too constricted and the viscous effects take over. This gives us an optimal nozzle diameter of 75% of the original diameter, which in this case is about 1.33 millimeters. This configuration is estimated to allow a maximum outlet velocity of 16.2 meters per second, a performance improvement of 25.7%, and that's not nothing. This new exit velocity increases our range from just over 7 meters to almost 9 meters, and it'll be able to hit a target meter diameter now over 5 meters away. Again, this is without air resistance, but regardless, the performance improvement just by changing the valve geometry is striking. It's hard to argue that this one at least helps somewhat in practice in the real world. Alas, an actual test of this geometry is outside the scope of this video, but I do intend to conduct one. So there you have it. Velocity. Look, here's the thing with fluid dynamics. Predicting the behavior of fluids is difficult, as gases and liquids are chaotic by nature. Their molecules are farther apart, they vibrate faster than solids, and can easily slip past one another. This is partly why there are so many abstractions, approximations, and assumptions when dealing with fluids. It's just the only way to understand it without delving into insanely complicated mathematics. I'm talking more complicated than I have ever encountered, and definitely more complicated than what is presented here. But one thing is for sure, if you want to build the best web shooter using fluid, you better be sure you understand how viscosity and pressure can affect a flow. Of course, web lines, after they've solidified, need to have certain properties in order to support something like swinging from buildings. But these properties, which we'll discuss next time, are much better described in a qualitative way, so don't worry, no math moving forward. Unless you like the math, in which case, welcome to the club, nerd. Oh yeah, a reminder that this is the second of 3 parts, and a must-watch guide to pretty much everything scientific about making web shooters. So leave a like so I'm motivated to make part 3. Now, be sure to follow me on Instagram at the.amazing.labs, and please support me on Patreon or buy my merch, the links for which are in the description below. The main reason to do that is so that this laboratory can be real and no longer just a virtual background. Oh, you didn't know this? I mean, look, it's not real. It's just a green screen. Basically, this real-life laboratory would be the research facility tackling the scientific problems I've mentioned herein. So yeah, if you're interested in these problems, be part of the solution. And the link to my Discord server is also in the description, so feel free to discuss any scientific ideas you might have. I might be listening. I thank you all for watching. Let me know if I've made any errors in the comments below. And please remember to stay safe and stay amazing. See you in the next one.